Then let's get the topic of today started. The F-test or ANOVA. Suppose that we want to compare the shearing stress of a propeller internal shaft. And suppose that we are making this propeller with this complex internal structure, the picture on the right. That's the internal structure. And of course, with this complex shape, we have to use metal 3D printing. But this is not the focus of this question. What we are looking after is the second part. Suppose we have the following 4 scenarios, okay? Scenario number 1 is we have one set of these propellers, let's say 5 or 10, and all of them, they have been manufactured by one machine, one printer, okay? No difference between the condition of producing one to another. The second scenario, we produce 2 sets of these propellers, 2 sets. They produced again by one machine, but this time we are testing a new extruder for this printer. So what we have, the data that we have, the first set is with a regular extruder. An extruder, if you don't know, with the printer, is that nozzle that pushes the material out. But imagine if you don't know a part of this machine that we've done some improvement. And then the second set comes from the improved. So the machine is the same, all the parameters are the same, except we have done some improvement. And then the third scenario, we have 2 sets of these manufactured by 2 different machines, totally different machine. And when I'm saying different, let's say 2 different brands, right? Not machine 1 and 2 being identical, 2 different brands. And scenario number 4 is exactly similar to scenario number 3, except instead of having 2 sets, here I said 3 sets, but maybe we have scenarios that we have, let's say 5 or 10 sets. Let's say we have 10 different brands and we want to test them. But for simplicity, let's stay with 3 sets of propellers, all right? So I hope you have a good now visualization of these 4 scenarios. The claim for each of these scenarios can be like this. For the first one, maybe the claim is that, remember, we are testing what we are testing, the shearing strength. We are testing the parameters of these propellers, and we have done the test and we average them. And maybe the claim for the first one is that the average, so let's say the claim is that the average strength is bigger than a value. Okay, that can be the claim. So for the second one, as Steve mentioned on Tuesday, it is a scenario of what we call it a before and after. So before and after. So the claim here can be that the improvement really improved the scenario, and like the improved extruder. So this one then can be the strength before is less than what we have after. Okay, so that can be the claim then. What about the third scenario? The third scenario, we have 2 sets. We look at the average. So the claim can be that one brand is performing better. Let's say we can say the average of one, let's show it by mu1, is bigger than mu2, like machine 1 is better than machine 2. It can be the claim. And here, average strength of the shearing strength of the propeller shaft, internal shaft. And the third scenario is exactly similar to the first one. And then the claim can be that maybe machine 2 is better than machine 3 or machine 1, but machine 1 is better than machine 3 or something similar. Like, or in other words, there is a significant difference between these 3 machines. can be anything. Okay, so these 4 scenarios, and this can be the possible claims. With these 4 scenarios, let's look at some numbers. Okay, scenario number 1, again, to remind you, produced by one machine. Scenario number 2, before and after. Scenario number 3 is 2 different machines, and 3 or 4 or more than 2 different machines anyway. So if I want to test these scenarios, my null hypothesis H0 for scenario number 1 can be something like, let's say, mu is equal to, let's assume 30. Why? Because our claim, remember we said it can be something that the average is bigger than 30. So our null hypothesis then is that maybe the differences here is by chance, and the null hypothesis is saying that no, this comes from a population that has an average of 30 megapascal. For scenario number 2, again, as you saw last day, what we will do, we make another column here, and it doesn't matter how, but we can say after minus before. Like here, we say after minus before, it's going to give me 2 here, 2 megapascal. It's going to be -1, and it's going to be 1, -1, and 0. And then we work with this data. Okay, so here our null hypothesis then is mu equal to 0. Why? Because our claim can be something that the X bar is bigger than 0, right? We say that there is an improvement, and here I'm going to show it by X bar D. So, and by D I mean difference. Like this column. Okay, so this is our null hypothesis. And scenario number 3 is easy. So we have a claim, maybe one machine performed better. Our null hypothesis then is mu1 is equal to mu2. It says that no, there is not a significant difference between these two, and they come from a population that each of them has a mean, but there is not a difference between these two means. And scenario number 4 is exactly similar to 3, sorry, except we have now mu1, mu2, mu3 for this case, but it can have more than 1 columns of data. Okay, so these 4 scenarios, this is something that we usually in a statistic, when we do a test, we may deal with. Now, we want to do a test, hypothesis testing, and it's concerned about means. Let's summarize them in this table, the steps that we need to do to conduct a hypothesis testing. Okay? So the first column are the 4 scenarios that you saw. And please pay attention to this page. If you can follow and understand this page, it means you're good for like conducting a hypothesis testing concerning means. So the 4 scenarios, the one mean, the 2 paired means, the before and after, the 2 independent means, and then K means, which in our example of printer, K was equal to 3. Okay? So, and I want you to have these 4 scenarios that I told you in your mind. Our null hypothesis, you saw the null hypothesis. So for each scenario, scenario number 1, mu is equal to a value. 2 paired, mu is equal to 0, and mu1 equal to mu2. And for the K means, as you can see, mu1 equal to mu2 equal to whatever mu K. And now we're going to be more like getting to more details. And so far, except with the last lecture, which Steve started mentioning about the sample size, Now we want to be more accurate, and we're going to set some rules, and we're going to follow those rules. And the sample size matters. So we are going to have two categories, large and small. When it comes to small, there are different arguments. Some people say 20, but to be more conservative, any numbers below 30 consider small. But if you read a textbook and they said 20, that's okay. And this number 30 is not just an arbitrary number. They plot, for example, the t-distribution or other distribution, and they realize when you get to that number more than 30, your distribution becomes closer to a normal distribution. And anyway, that's the job of the statistician and mathematician. We leave it to them, and we follow their rules at what they say. Okay, so this is then the scenarios that we have. And now we want to do the test hypothesis testing for them. Hypothesis testing always has 3 steps. Step number 1, you will calculate a test statistic. Step number 2, you find a critical value depends on your alpha level of confidence or significance level. 5% is a normal value, but most of the time, like the question gives this number to us. If they don't, then 5% is very common. And then step number 3, you compare the test statistic that you find in step number 1, compare it with the critical value, and either you reject your null hypothesis, okay, or you accept it. Moving back 1 step, if you accept your null hypothesis, it means that no, for example, scenario number 3, mu1 is equal to mu2. There is no significant difference between these two. Or in scenario number 2, you say, no, sorry, mu is equal to 0. And by the way, here is mu d again. And it means that there is no improvement. But if you reject your null hypothesis, automatically you are saying, no, there is a significant difference. For example, there has been some improvement. Okay, that's the steps, easy and straightforward. It's from now on, it's just a bunch of formulas, right? In step number 1, you calculate a test statistic, which is a formula. You saw it for the very first one sample, large. So what we will do, we assume that data are normally distributed. This is our formula to calculate z, x bar minus mu divided by standard deviation of the mean, and n is the number of samples, okay? And so you find that value here. And z alpha, easy, you go to the standard z table, and based on alpha, you will find z alpha. And by the way, instead of finding a z alpha, you can find the p-value. These are exactly the same, and you realize it. You saw it in tutorial and so on. And then you compare them. So if the z, your test statistic, happen to be on a tail bigger than this z alpha, then you reject it, and then the rest of the story. If your samples are small, everything is the same, except now, instead of a z distribution or a standard normal distribution, we look at the t distribution, okay? And instead of finding test statistic, the letter z is just replaced by t, and the formula is the same, except here now, s. That's the standard deviation for the samples that we have, not for the population like this one. And again, you saw it in your midterm 1, the number of samples were small, 18, I believe, or 15, but we gloss over it. We wanted you guys to try, so now you realize that if you want to do that test properly, you need to do a t-test. Not that you get a wrong number, but t-test is more conservative. So Steve explained the t-test with details, and you know how to do the t-test, except we mentioned the degree of freedom, and I'm just gonna highlight it, and next slide, I'm going to explain the degree of freedom. But for now, accept that the degree of freedom is just a number n-1. But I highlight it here, so I promise you next slide is on degree of freedom, because I saw on Tuesday that many questions asking what is degree of freedom. So, and t-distribution, so Steve clearly showed it last day that it's more conservative when n is small compared with the normal, standard normal distribution, like it's fatter, maybe not a good term, or thicker on the tail. But as the n becomes larger and larger, or df, degree of freedom, becomes larger, or number of our samples become larger, then it gets closer to a normal distribution. Now let's get to the two paired means. Again, we have the same scenario of large and small. And our procedure is exactly the same as one mean, except this time we work with the paired data. We work with the x bar d, and the standard deviation of the difference. And also this should be d, okay? So n is again the number of samples, but the data that we will work with is that the third column. We work with the differences. I'm going to move back one slide, right? Forget your first column of data, your second column of data. You're working with this after minus before. And your hypothesis mu is equal to 0. That's why when you look at this formula, there is no mu in them, right? It's exactly similar to the one above, like the first row and second row, but mu is 0, so we set mu is equal to 0. And we will do the exact same step. Nothing is different, okay? I'm gonna quickly check chat to see if there is any question. So, Troy is asking, larger sample size makes t-test too conservative. If it is too large, there is not going to be any difference between t and z-test because the distribution becomes closer to the normal distribution. That's why if n is bigger than 30, it doesn't matter which one you use. But always t-distribution is a little bit conservative. And the reason that the guy invented the t-distribution is because he was working for a brewery, and in a brewery company, if I'm not wrong, and the sample size are always small. So he invented that. And t-test, a student test also people call it, because that person called him a student. Okay, so let's get to the third row, the two independent means. Two different 3D printers, two different machines. The sample size is large. Then still we use the Z distribution, except our test statistic has this formula. And where it comes from, if you look at the one at the top, the first one, it's exactly similar to that one, except mu now is 0. Why? Because our null hypothesis is saying mu1 is equal to mu2. So you have mu1 minus mu2 here, right? Mu1 minus mu2, but because of our hypothesis, it becomes 0. And combining the standard deviation has this formula, which again, we don't get to the algebra where it comes from. If you are interested, you can easily find it. It's easy, it's on internet available. And everything else is the same. And if n is small, everything is the same, except the t has like this weird formula. I try to write it down something similar to z, except it has this sp, which has this formula. And the proof, I believe it's not in your textbook, but it's many other textbooks available on internet. You can find where it comes from. For us, we just use it. And N1 and N2 can be different. Okay, so you have two sets of data, and the number of samples can be different. Usually they are the same, but it happens that they are if they are different, then you use that. Do not forget your degree of freedom now has n1 plus n2 minus 2. Okay. Here, your degree of freedom, like in this scenario, is still n minus 1. Although you have two sets of data, but it is n minus 1. Why? Because we are working with just one column of data, which is the differences. So this is what we had so far, and I hope it's clear. And what we are going to do today is this last one, the k-means. And it can have any size, small or large. We are good. And this is what it looks like. And this will be the topic of our today. Something that it's called F-test, which I will say why people call it F-test. And it concerns about the variance. So it looks at the variance now. So maybe that's why it makes it a little bit complicated, because now instead of means, we will work with variance. And variance between the groups and within the groups, which I will explain. Okay? So, but the procedure is the same. We will find a test statistic, which we call it F. Then we will find a critical value similar to Z and T alpha. We have to set an alpha, a confidence level. And then we calculate F alpha. Instead of a Z distribution and a T distribution, we are going to use a different distribution, which is called F distribution. A little bit is different. And similar to T distribution, it has degree of freedom as its parameters, but it has 2 degrees of freedom, like 1 df1, 1 df2, and I'll get to that. Okay, that's the topic that you're going to compare, but the procedure is the same. So everything's for doing a test concerning means has been summarized in this table, and you should keep this table, and always when you do the test, refer back to it. So, as I promised, before I get to the F-test, what is degree of freedom? So if you ask a mathematician, you will get this definition, and I'll let you guys to read it for a moment while I'm drinking some water. It's a fancy definition, right? But does not really make too much sense unless we are doing some advanced algebra in vectors, matrix things. I'm gonna quickly check chat. Okay, I will get back to that summary in a moment. Let's focus on the degree of freedom, then I'll get back to the question in the chat. Okay, so a mathematician then definition is not really that useful for us. Let's ask a statistician. Well, probably they are gonna tell you it's none of your business. No, nothing like that. They say, who cares? Just perform the statistical analysis. And as long as you know that the degree of freedom is a parameters and it is n-1, or maybe in a case of F-tests, it has this form, who cares? But we are engineers, right? And we like to know what is really a degree of freedom. And on Tuesday, I noticed in a chat, several people asked, is it similar to dynamics? So I decided to explain it dynamic-wise. Maybe it's easier for us to understand it. So in dynamics, so engineer then, dynamics. Forget about data. In dynamics, let's say if I have a box, and for simplicity, let's say a 2D in 2D, let's say on our table, and we see, look at this box. So all of us, we know how many degrees of freedom this box has, right? Right away, we know that this box can move to the left or right. It can move ups and down, and it can also rotate. So the degree of freedom for this guy then is equal to 3, all right? To define its position, I need 3 values. But what if I constrain this guy and I put this box, let's say, just again for the sake of discussion, let's say I put it inside a rail, maybe or in a slot. Something like that. Now, what is my degree of freedom? I'm sure all of you guys are going to say 1. So my degree of freedom now is 1. Why? Because I cannot move it ups and down. I cannot rotate it. It can just move in one direction, left and right. So in fact, what I did, I constrained it. And the number of constraints here is 2. Still, sum of these 2 numbers is 3, right? But I have a constraint. This is what we know in dynamics, that something has some degree of freedom, and which we know what it is, and then we put some constraints, it reduces its degree of freedom. Let's get to the data. Again, for simplicity and for the sake of just understanding the concept, assume that you have, let's say, assume, let me write it down. You have a set of, or let's say a data set of 5 values. And let's assume that you are not estimating anything. Okay, so you're not estimating anything. So then we can say each value can take any number. Right? Let's say as a placeholder, can I get rid of that? Yes. Let's say I have maybe 5 placeholder for 5 numbers. One, two, three, four, 5. Okay. So I can have put any numbers here, 7, maybe 8, let's say 5, and then 9, and then maybe 1. So since I'm not estimating anything, this 1 can be 11. Nobody cares, right? But now let's say, but suppose you want to test the population let's say the population mean with these 5 numbers. These 5 values. Then we know if we want to test the population mean, there has to be a relation between the mean. So in other words, maybe I'm free to choose the first 4 numbers, but I'm not free to choose the last number. Why? Because we know that let me get rid of that. We know that there has to be a relation between these guys. So we know x bar has to be sum of x divided by n, which n here is 5. And again, for the sake of discussion, let's say somebody asks us that x bar is 7. We are testing something, okay? And we are using this data for an estimate. Then if my x bar is 7, I'm not allowed to put any number here. This has to be equal to 6, okay? So I have a constraint here. So a constraint. So I will say then my degree of freedom It's not 5, it's 5 minus 1, it's 4. So in other words, simply degree of freedom is equal to the number of observations minus number of required relations among the observations. Like here, when we do the t-test, the required relation among the observation is that we want the x bar to have a certain value. That's why we have one constraint. Okay, hope it's clear. If it's not, this is the best I could do, because if you Google internet and search for degree of freedom in a statistic, you either get the first one from the mathematician or the second one. But again, I realized that we like to somehow relate it to dynamics, which is sort of we can, and this is what we can get out of it. Let's see if there is any question for degree.
Can I stick my oar in for a second here?
Absolutely, go ahead.
The degree of freedom concept also applies to thermodynamics. And the way we normally think about it there, it's the number of properties that you need to independently specify before everything else is fixed. So for an ideal gas, you would have to specify 2 properties, or for any single phase substance, you specify 2 properties. But if you have two phases present, like vapor and liquid, you have that effectively is another constraint. And now the degree of freedom would go down to 1. In other words, you would pick the temperature and then you look up the saturation pressure from the steam tables. So, so generally you can think of the degrees of freedom as the number of pieces of information you need to totally specify the state of the system. Same thing, but a little different.
Exactly. No, thank you. Thanks, Steve. So, yeah, so you saw it in thermodynamics and also in dynamics, and with the numbers, the same concept. And so I hope your mind now is free of this understanding of degree of freedom. And now you just like a statistician, you use the formula. Okay, so with that, let's then start the F-test. And our objective here is that after today's lecture, you guys should be able to do an ANOVA. As I said, I like the sound of it. Sounds fancy, right? ANOVA. Analysis of variance. And also it's known as F-test. And the purpose is comparing the K groups of data. K can be 3, an example of the 3 printers that we had, or can be 10, any number, doesn't matter. And each group can have any sets of data, small or big. I will explain the steps in a moment. And please note that here we're going to focus only on application. We're not going to go to the algebra and proof of the formula. But if you are interested, there are textbooks that explain it. It's not in your textbook. F-test is not in your textbook. It's a bit daunting, and but I'll try to explain it in a very simple manner so you guys then know how to apply it. But if you like to go further and know what is behind it, then that there are books and that which you can go and study them, which is beyond the scope of the work in this course. More, I guess, I believe there are math in math department, there are courses specifically for this. And the YouTube video that I posted, those are from the student of a person who invented the F-test. Like brand, let's say first, how can I say it? Coming from a student of the person who invented the F-test, the original, very original. And he explained the concept behind the method. But again, he didn't go to the proving the formula or anything. So if you are interested in knowing about the F distribution, like its equations, it is in this link. And for the table, which we are gonna use the table a lot, here is a good, there are many links available, but this one I found it, like it's pretty accurate and neat. Okay, so with that in mind, let's see what is F-test. And always I like to convey my message using examples. Let's get back to the examples of the printers for our propellers. And keep in mind, we are focusing on scenario number 4. Scenario number 4, we had 3 different printers. And suppose that we have, like, just for the sake of discussion, I put these numbers there. They are not real, okay? Just wanted to convey my message. In example number 1, let's say we have these numbers, example number 2, bunch of other numbers, and example number 3. And I want you to focus on example number 1. Look at just the data from printer 1 and tell me what you notice. If somebody gives you this number, what would you say? Like you can see 10, then you'll see 12, 18, and then 28 and 36. And I put them in order so it's easy for you to just take a look at numbers. What would you say if you see these numbers? You can type it in the chat. Huge variance, true. So see, now you guys are paying attention to variance. That's good. And that's what F-test is about, looking at variance. And Troy, you're right. And most of you probably you guessed that. If you look at the first column of data in example 1, you see huge variance, 10, 28, 36, right? Printer number 2, similarly, 11, 23, 38, and printer number 3, the same. Large variance between each group. Let's say, just again, for the sake of discussion, if I plot the PDF of this data, maybe their population, then can I say that the first printer maybe comes from a population that has a huge variance, like maybe a normal distribution, but it's very, like the width is very large. And then the second one, let me plot it by red, maybe something, let's say, maybe like that. And then the third one, maybe I color it by green, maybe something like that. So to keep track, blue, red, and green, this guy. So what we notice, if we look at the mean of this data, like the blue printer, maybe the mean is around here, and the red one is around here, and then the green one, maybe somewhere around, I don't know, here. All right. So what I can say then about this data, again, visually, without looking at any formula or anything, I noticed that the variance in each group is huge, but within each, between groups, like if you look at printer 1 and 2, the variance is not that, like 10, 11, 12, 14, 18, 19, 28, 23, 36, 38, and similarly between 2 and 3, right? So maybe I can write down that the variance, let me write it down a little higher, variance between groups is small, but variance within groups is large. Can I say that? I guess this is something that visually we can say. What about the second? Let's now look at the second example. What would you notice about these numbers? I just want you to take a look at printer 1 and tell me what you notice. probably you can guess the variance, yeah, as you mentioned in the chat, the variance in the first printer is very small, 10, 11, 12, 13. Printer 2, if you just look at printer 2 alone, variance is very small. Same with printer 3, but going from one printer to another printer, the variance is large. I guess you got the idea. If I plot the PDF, then what I will notice, and again, let's be consistent, the blue one, maybe this is their normal distribution. And then this guy is the red one. And this is the third printer. So if I look at their mean, then, so this is for the first one. Second, and this is the third one, right? So let's then write down the same sentence that we wrote for this guy here, just out of laziness. So this is for this guy, this is for this guy, or let's move it a little bit there. No. I don't want that things to move. Our life becomes difficult with online teaching. I was more comfortable teaching it on a board. So what we need to change here is it is large and this guy is small. Okay. And obviously, if our claim, let's say our null hypothesis, if we get our null hypothesis H0, I'm going to write it on the top here, is that mu1 is equal to mu2 and equal to mu3, right? This is our null hypothesis. This is what we are looking after to test. Looking at the first group, just visually, we can say that no, the difference between these is just by chance, because the variance between groups is small, but within each group, the variance is so large that we cannot really say there is a significant difference between them. But for the example 2, obviously there is a significant difference, right? You can see it visually. So can I then say, if I calculate the ratio of a number, for now let's call it f, but this f is the variance between groups divided to the variance within groups. And I'll do the same for this guy. So what we'll notice then is in scenario number 1, in example number 1, this is large, f is large. Or I'm wrong. Variance between groups is small, so this is a small number divided by large number. Sorry, it's very small. We're dividing a small number to a very large number. F is small, here f is large. So here you have it. This is the f test. You calculate this value of f. If it is small, you reject your null hypothesis. If it is large, you accept your null hypothesis. Or I said it the opposite way, right? Yeah, so let's say it again, sorry. If f is small, okay, if f is small, you accept your null hypothesis. You are stating that there is not a significant difference between them. So mu1 is equal to mu2 is equal to mu3. But if f is large, then you would say, as clearly you can see in this visually on this example, you say, no, there is a significant difference between mu1, mu2, and mu3. All right. So this is the F-test. But let's get to the third example and tell me what you notice about these values. Just spend a few seconds and tell me what you see about these numbers. Anything? I'm gonna check chat, maybe somebody says there. So that's a good point. F is around 1. The variance is small for everything. So that's true. Yep. So as you can see, for example 3, it's not really obvious. It's not like example 1 and example 2. And as I said, example 1 and 2, I just exaggerated it for the sake of discussion. I use these values so you could obviously see it. So the differences is not obvious, not obvious. Besides, when we do the hypothesis testing, using just the word large and small are not really very scientific, right? What is large? Maybe for somebody, small means 2, 3, but for someone else, it's 100, right? So we need to, so it's not a judgmental call. We need to have a systematic way to conduct these F-tests. And this is where we need a distribution. So we can find a critical value, similar to Z or T test. And this is where this guy, Mr. Ronald Fishers, discovered these things. And I have to admit that I didn't like a statistic too much. I used it in my work. Most of my work is in industry, and I use, it involves a lot of tests, of course. Whatever we manufacture, we need to do some tests to tell to customers, and we use always a statistic. And always I didn't like a statistic because I thought, okay, it's just an average. You just look at the average and a standard deviation. That's all it is. Until I studied carefully the F-test. And then after that, I started liking a statistic. And maybe, hopefully it will happen for you guys. And observing students from previous years, getting to F-test, students start liking a statistic. And then when we get to the machine learning, they start loving it, maybe too much, that they hate the first part. But anyway, you need this first part before getting to that second part. But anyway, this guy, he quit his job, his main job. He's a biologist, I believe. He quit everything because he wanted to figure out this F distribution. And he invented this method and the formula for a F distribution. So some people, in respect of his name, call it a Fisher distribution, and that's why the word F comes to play, because of his family name. So you guys are lucky that I haven't invented any distribution, because my family name is long. So maybe many of you don't know. You don't know how to say my family name. It's very long. And imagine I had a distribution. What would you call it? Maybe you can practice it later. Okay, so let's get to the F distribution. F distribution is skewed, as you can see from this picture. So it's not symmetric and nice like a normal distribution. It relates to chi-square distribution or chi-square test, which is something we will discuss in future lecture. But for now, just if you read somewhere, it relates to chi-square. And it has this, again, a skewed shape with this long right tail. And the parameters involves like D1 and D2, like here we'll see, 2 degrees of freedom. So D1 and D2, they are degree of freedoms. So it has 2 parameters then. T distribution had 1 degree of freedom, like 1 parameter. It has DF1 or D1 and D2. And X is our of course, variable, and then the PDF that we see here. Okay, so again, since we are going to do a test, hypothesis testing, it involves calculating the area. If you look up the equations on internet, the equations are very ugly. Ugly is not a good word. It's very complex. Unlike Gauss equations, this one is a little bit complex, and integraling it, it's a pain. So, but anyway, we need to find, let's say, the area depends on the alpha that we are testing. Let's say for a certain alpha, we need to anyway calculate. So this is the area is the alpha, and we need to calculate F alpha. So luckily, people tabulated this, and it is available on internet on this link. Something that you need to keep in mind, again, it has two parameters, df1, df2, okay? So whenever you want to find the F alpha, so first of all, you need to know your alpha. Let's say for this example is 5%, and when you look up the table, be careful. On the corner of the table, it says for which alpha you are testing it, like 5%. And then the rows are the df1, the columns is df2. But what is df1 and df2? Okay, this is the question that maybe is more important. Let me write it down here. df1 is degree of freedom between groups. So, or like a statistician, it is just k minus 1. Let's say you have 5 groups of data to test, it is 4. In the example that I just showed you for 3 printers, we had 3 groups of data, right? Let's move back. We have 3 groups, k is 3, so our df1 is 2 then. So df1 is k minus 1. And what is df2? df2, we can say it is the total degree of freedom between all the data. So it is df2, which is n minus k. Don't forget, n is the total number of data or observation. So in other words, n is n1 plus n2 plus nk minus k. Obviously, if n is equal, like all the groups have the same, so it's going to be then kn minus k. So if in a textbook you saw a formula like that, don't get confused. It's because of case of all equal with equal n. All the groups, like in the example of 3D printers, we have the same number of data. Okay, this is about the table then. You read your df1 and then df2 and you find the number. That easy. Like, let's say somebody asked me that I have a df1 of 8 and df2 of maybe 10. This is my critical value. Okay, so that's simple. Now, this is the steps involving doing the F-test. Similar to that summary table that I showed you, 3 steps. Step 1, step 2, step 3. Step 1, calculate F. Step 2, find critical value or F alpha from the table. What do you need? You need alpha, you need df1, and you need df2. Okay? And step 3, you compare them. Simple as that. How would you compare them? Oops, what is this? So similar to Z or t-test, let me just graphically show it. Let's say if this is our F distribution and based on your alpha, you find the critical value. Let's say the critical value is here. Okay, this is your critical value. Now, so this is F alpha. So now either you are, let's say here, this is your F. This is your F. This is this F, right? Or you are maybe in a tail here. So if you are here, then you reject H0 and you accept H0. If you reject H0, then you would say a significant difference between the groups. Okay, so this is how we do it. Hope it's clear, but now a big question remains. How do we go and calculate this guy, right? In theory, looks simple, but how do we calculate it? Let's learn it by doing one example. So I'm gonna stop here for a couple of minutes, let you guys read this example, maybe go drink a water or something. I'm gonna do the same. And let's come back in 3 minutes, or maybe 5 minutes. Yeah, so it is 32. Please be back in 4 minutes. Let's start at then 4 or 5 minutes. And while you are doing that, I'm gonna stay here to see if there is any question. And then we are gonna solve this example, and hopefully solving this example, you will find out how we do an F-test. And I'm gonna stay in the room if you guys have any question. Also, I'm gonna check the chat to see if any question is left. I guess this week is very busy for midterm. How many midterm do you guys have? I've heard like mechatronic students have 3, I guess. Oh, one right after this. Okay, I cannot compete with that. So that's why I can see not so many students in the class. Okay, but we're almost done. Let's solve this example and then we're good to go. Okay, so if you didn't have a chance to read it, please carefully read it and let's go over it together. A manufacturer that is making toilet paper, and you know it's a very well-paid job if you find a job in a factory making toilet paper, go for it. So they, like the engineer believes that the amount of hardwood, which is usually expensive, it has an effect on the strength of the paper or toilet paper. And you may say, who cares about the strength of toilet paper? Apparently, it's a big thing. I didn't know before that, but it's a big thing. And how people measure the strength of a toilet paper, believe it or not, it's very, very similar to doing a tensile test. I have a short video here to show you. Let me play it. So of course, the forces are very, very small, but it's, as you saw, is very similar to the tensile test. Now you may say, for our capstone, we should have done a test with a toilet paper. It's easy, right? And it goes to our CV, and then we can find a very good job later, especially in BC. Anyway, so now that we know how the test has been done, and this is the values, and so this is the 4 groups of data that we have, 5%, 10%, 15, and 20%. We don't care about these like values for now. Don't get confused by these 10%, 5, 10, 15, and 20. Just we look at 4 groups of data and we want to compare them. Group 1, Group 2, Group 3, and Group 4. So our K here then is 4. All right. So immediately you can say my degree of freedom 1 is K minus 1 is 3. So intentionally, you see there's some boxes here is empty. No data here, no data, no data, no data. Maybe when the engineer was doing the test, something happened to the machine, or like on day 1, he did the test, the last test, he just ignored it. And day 3, he didn't have enough time. So that's fine, totally fine. So we say N1 is then 5, N2 is 6, N3 is 4, and N4 is 5. So total N is going to be N1, N2, N3, N4. Give me 20, right? So my DF2 then is N minus K is 16. So this is some numbers that I have. To perform the F test, we need to find F, right? And F is equal to the variance between the groups and the variance within the groups. Our goal is to find this number. So to do it correctly, I suggest we write our table like this. So you write your table like this, you open another column. In column 2, you just simply calculate the square of each. So this is just simply the square. So let's quickly calculate the square. So 225, it's a good checking your math. So it is 100, 169, and please correct me if I'm wrong, 196 and 169. This guy 289, 144, 324, 169, 225, and 144. 121, that's easy, and that's for that. What about this guy? 100, 144, 64, 49, 81. Okay, As simple as that. Then the last row, just sum all of these data. So sum of this guy is going to be 65. I've done it before. 859, 87, 1,295, 40, 420, and this guy 46, 438. So if we make this table correctly, the rest is just putting these numbers together, some algebra. Okay. So the first step, like you see the formula on the right, we just follow those formula. Okay? So sum of the square between, like the first things that I'm going to calculate, it is sum of this guy squared, so don't confuse it. Then it's going to look like this is equal to, it's equal to 65 squared divided by 5, right? 87 squared divided by 6, then 40 squared divided by 4 plus 46 squared divided by 5 minus the second guy is sum of the total square. So it's going to be 65, 87, 40, 46, all of them squared, divided by n, which is 5, 6, 4, 5, or 20. It gives us 97.5. So having this number, then I can easily find the variance between groups. Divided by, we have 4 groups, so it gives me 32.5. This is our first number, the standard deviation between groups. That's the numerator, okay? We'll do the same. First, we need to find sum of the SI, right? So this guy is equal to sum of them. So like for this one, it is, oh, we have that number here, 85.9. Oh, let's do it for one by one. Let's say SS1, sorry. SS1 is gonna be 859 minus 65 squared divided by 5. Am I right? Yeah. It is this number, sum of this number, which is here, right? And then the square of the sum, which is this value, divided by n. So that gives me SS1, 14. We'll do the same for SS2. Let me write them down a little further. Okay. We'll do the same for SS2. I'm going to leave it to you to check my calculation later. SS3 and SS4 is going to be 14.8. And here we just add these 4 numbers, SS1, SS2, SS3, SS4, which will give us 82. Let me use another color, 82.3. Okay, so as you can see, nothing really special. It's just adding a bunch of numbers. So now we can successfully find the variance within the groups, which is going to be 82.3 divided by 20 minus 4. It gives us 5.14. So this is our second numbers. We divide them, 32.5, divide by standard deviation within groups, 5.14, gives me 6.32. So this is my F. Okay, now let's do the last step, finding F alpha. So we have DF1 and DF2. So DF1 is 3 and df2 is 16. Sorry for the mistake. So if it is 16, then let's go one more time and we will find f alpha. It is not then that number here. So this is 16. So it's going to be then 3.23. Let's move back. 3.23. Still, we are rejecting that.